This conference will now be recorded.
So, very good evening, students. Today we are going to complete discussions on this modern physics part. Then we'll go for the optics in the next class onwards. So today I have actually focused on only the semiconductor part. In the sense, today we'll take only uh, logic gates, transistor, and diode problems. And all these problems are actually from various competitive exams, mainly IIT JEE mains and AIEEE, etc. So we'll start our discussions today with this problem. So we can see there are two diodes over here. Okay, they are connected in series with 5 ohm and 10 ohm resistance respectively, and these two branches are parallel to each other. And this gap between A and B, there will be battery. Now we'll see in the question what it is said. It says a 2-volt battery is connected across AB. 2-volt battery is connected across AB, this gap, as shown in the figure. The value of the current supplied by the battery when in one case battery's positive terminal is connected to A. So first case, A is positive and B is negative. Okay, that means this side this and this side like this. So this is the first case, and in the second case, in another case, positive terminal of the battery is connected to B. Okay, and negative terminal obviously to A. Now you have to find out okay, so respectively B. So here the value of the current supplied by the battery in two cases respectively what? See, the options are 0.4 ampere to 2 ampere. That means in first case, when A is positive, that time it is 4.5 ampere, and when the battery it was reversed, that means battery positive terminal was connected to B, that time the current in the circuit was flowing at 0.2. So like that you can read all the other options also. So here you have to find out which one is the correct option here. Okay, so let me see what happens in this particular configuration when A is positive. So when A is positive, then see this diode is reverse biased, right? Reverse biased. Okay, whereas this is forward biased. And diode in reverse bias does not conduct. That means you have now in this case only this circuit. This diode is there is a 5 ohm resistance. Okay, and you have a battery connected to this, and this battery is 2 volt. Then what will be the current in this circuit? So current will be 2 volt divided by, so V by R is equal to, see, V by R, voltage by resistance will give you the current, right? So V by R, this will be in ampere. So it is, you look here, it is 0.4 ampere. Okay, in the next case, or the second case, we say second case, see, second case will be just opposite, exactly opposite. So if this is connected to negative terminal, if this is connected to positive terminal, so this will be forward bias, FB, and this will be RB, reverse bias. Okay, then this one will not conduct, so I'll have only this circuit. Look, this is the diode and resistor connected to this, and this side is negative, this is positive terminal of the battery, this is 2 volt and this is 10. So what will be the current in this case? In this case, voltage by resistance, right? So 2 by 10, this is volt, this is ohm, so this will give you ampere. Okay, 0.2 ampere. So what are the, like, among these options? Fourth, like, see, the first option itself is correct, so first option is correct. Okay, so this is how you have to see, you have to solve the problems if you have more than one diode in any case. Okay, let me give you one more example. Let me just take you through another example of this kind of diode problem. Okay, so I'll just go to the last page. Okay, similar type of diode problem. So the circuit has two oppositely connected ideal diode. I'll just draw the circuit diagram first. You have, oh, I'm sorry, just a minute. I have one diode here. Okay, this say D1, and another diode connected in the opposite direction. This is another diode along with series resistor. This is D2, and see, this resistance in series with 2 ohm is, this is 2 ohm. Okay, and this resistance is 3 ohm. 3 ohm. Now there is another resistor which is connected like this in series with the battery. Okay, battery negative terminal is here and here it is positive terminal and connected like this. So the now question is that what is the current flowing in the circuit, in this circuit? If I read the question says the circuit has two oppositely connected ideal diodes in parallel. What is the current flowing in the circuit? So options are given. Obviously, I have not given this resistance. This resistance is 4 ohm and this battery is 12 volt. Okay, so options are 1.701 ampere. Second option is 2.0 ampere. Third option is 2.31 ohm, sorry, ampere, and option fourth is 1.33 ampere. So you have to solve this problem. So how do you solve this kind of problem? So you have to see which one is, see, this is negative, right? Negative terminal, and this is positive terminal. So you have to see out of these two diodes, which one is getting like reverse bias, which one is getting forward bias. So this guy is reverse bias, and this guy is forward biased, FB, right? So which one is going to conduct? D1 is going to conduct. D1 is going to conduct. Okay. So if D1 is conducting, then see, what is the total resistance in the circuit. Okay, so we have to see here total resistance in this circuit. See this, you can just think of uh, just erasing this, because this is not there now, since it is not conducting. Okay, it is not conducting. All right, so you can just ignore that. So you have this circuit now. All right, so you have resistance 6 ohm, right? And you have how much? Battery voltage is 12 volt. So 12 volt by 6. So it will be 2.0 ampere. Okay. So this is the answer. This is very simple. So no need to worry too much. This kind of problems you can solve very easily. If diode is there, you just see which one is forward bias and which one is reverse bias. Okay. In that way you have to solve. You don't need to think like how much current is going through this and all those things. Like there may be diode equation for current. Since this is the ideal diode, you can think that the whole current is flowing, okay, when it is forward biased. All right, so this is how we have to go with the first question. Now second question, this is also very important. This is from the application part of Zener diode. You can see this is Zener diode. This is a voltage regulator, DC voltage regulator. Okay, DC voltage regulator circuit, if you remember. Okay, this is DC voltage regulator circuit. So here the question is the value of the resistance, resistor RS needed in DC voltage regulator circuit. Here, so here you can see the input voltage is VI. This is the maximum input voltage it can provide to this particular circuit. So it, see, that means you know the total voltage across these two guys, two guys will be VI, right? Now the question is you have to find out RS. Let me give you the options. The options are very interesting options are given. If you look, this is VI, that means input voltage, minus VL, voltage in the load, and then N plus 1 into IL. IL is the current which is passing through the load. This is load resistor. Okay, RL. I'll explain what is the how it works. Then second option is the same with positive sign here. Okay, option C is VI minus VL divided by NIL. Okay, and the fourth option is VI plus VL divided by N into IL. So these are the options. Now let me tell you how it functions. See, when actually voltage regulator means what? DC voltage regulator means what? So regulator, you might know this we generally use in our day-to-day life. When there is a power fluctuation, to save the appliances or to get uninterrupted supplies input supply. For the appliances we use DC regulator or regulators. Okay, so in this regulator circuit, generally what happens, this input can fluctuate. Okay, but the same is, so if we directly use this input Vi to the appliances, then it may not work, sometime it may get damaged also. So that's why the voltage across the Zener diode, this VL, this is always stabilized voltage. Okay, VL doesn't change at the breakdown. If you remember, the Zener breakdown voltage is always, this is actually Zener breakdown voltage VB. See, in the reverse bias current will be, so current is changing like anything, but the voltage, breakdown voltage, is not at all changing. Okay, so at the breakdown region, if we use this Zener diode over here at the breakdown region, then voltage doesn't change even though current changes. So if current changes, okay, even if current changes in this diode, voltage drop across this or voltage across the diode doesn't change. That's why this particular voltage across this diode can be used as a stabilized DC voltage. Okay, so how this input voltage is connected? See, this is connected in series with this RS and this particular diode, Zener diode, and see, this means it is, suppose it is sending a current, some I current, total current I, it is getting, say, total current I is flowing through RS also, so it is getting branched into two parts. One is IL, it is going through this uh, load resistor, and this fraction N into IL, this is going through the diode. That means, you know, the total current which is passing through, I say IS is actually this one, IL plus N into IL. This is the total current which is flowing through the RS. So I have to find out what is RS. So look here, this total voltage is dropped across this RS and this voltage, right? This diode voltage. So diode voltage is VL, we know that. So I can write this VL plus VS. S means voltage drop across this resistor. Okay, resistor VS is equal to total input voltage Vi. This I can write. So Vs I can write Is into Rs. Okay, and this I can write Vi minus Vl. Okay, now I have to find out what is Rs. Rs means Vi minus Vl divided by Is. What is Is? Is I know here, n plus 1 into IL. Okay, so I can just put the value of Is over here, then we'll get the value of Rs needed for this particular regulator circuit. So n plus 1 into IL. So this is the answer. We have this option, the first option itself. This is the option. Okay, I hope you have understood this DC voltage regulator. See here, when the current is flowing, like current is increasing through this RS, actually current is increasing through this also, but voltage is not changing across the generator. This is the property, special property at the breakdown region. That's why Zener diode is used as the breakdown at the breakdown region, and we have very great applications of Zener diode, especially in this regulator circuit. Okay, all right, we'll go to the next question. This is a very simple question, but this, see, I'll just for your information, this is actually JEE, IIT JEE main 2015, IIT JEE. Okay, this is the question from IIT JEE main 2015, and the question now I'm going to discuss with you. This is also from some previous year's question. This is also from 2015, IIT JEE JEE main 2015. In an unbiased NP junctions, I should write PN junction anyway, NP junction, PN junction also you can say. PN junction, electrons diffuse in N region, from N region to P region. Electrons diffuse from N region to P region. So what is the reason for that? Because electron travel across the junction due to potential difference? No. Electron concentration, this is diffusion happens only due to concentration gradient. So electron concentration in N region is more as that compared to that in the P region. Okay, that in P region. So this is the correct option. Only electron moves from N to P region, not vice versa. This is not a good answer or good option for the question. Holes in the P region attract them. This is also not true. So only true is this one. Okay, concentration gradient. Diffusion happens due to concentration gradient. Concentration gradient. Okay, so that's why the second option is correct. Now we'll solve this problem. This is from transistor, not very great or troublesome problem. This is also a very simple problem only. For a common emitter configuration, so this is also from 2000, actually IIT JEE 2016. So this question says, in the common emitter configuration, here it is alpha and beta. You know, alpha is current gain. Alpha is given by IC by IE. And beta is also current gain. Okay, this is obtained as, so these are all DC current gain. Here we are writing, that's why IC by IB. So this is IC by IB, beta means. Okay, now you have to actually choose the incorrect relationship between alpha and beta. Alpha and beta are having usual meaning. I have written the meaning. Okay, so in one case IC is equal to beta IB, in another case IC is equal to alpha into IE. IE means emitter current and IC means collector current, IB means base current. So you look, I can write IC is equal to, IE is equal to IB plus IC. This I can write, isn't it? Because whatever charge carrier supplied by emitter region, these are actually getting, like, because of the charge carriers, it is producing two currents, IB and IC. So we can just Divide both sides with IC. IC plus 1 here. See, look, IC by IE is alpha, so this will be reciprocal. Here also it is IC by IB means beta, so this is also plus 1. Now we have got this. See, we have to find out first what is the correct option. See, the D option is correct here, right? So we can see, first of all, we will see which are the correct option. Then it will be easier for us to find out which one is incorrect. Okay. So we can see that 1 by alpha is equal to 1 by beta plus 1. This option is going to be correct. Now we'll see what else can be correct. We can simplify this particular expression itself. So you can write 1 by alpha is equal to beta plus 1 by beta. Then we can just get the reciprocal. Alpha is equal to beta by beta plus 1. See, there will be some, okay. So this is again true. We can see. So these two options are correct and other two options are incorrect. Okay. So therefore this option is correct, and this option and this option, they are not correct. Okay, we have got which are incorrect relationship. Okay, now we'll go to the next question, fifth one. So here you look, A, B, C, D are 4 inputs given to a gate. So gate is not specified here. We have to find out the nature of the gate, whether it is NAND gate, sorry, AND gate, OR gate, NAND gate, NOT gate. So A, B, C, D are inputs and their nature, how they are varying with time. So this is the time axis, and let us say this is voltage. This is voltage. Okay. So voltage is changing with current with respect to time, and this is the output. You can see this is the high output and this is the low output. I can say this is high, okay, and this is the low. Okay, so here you have to recognize which gate it is. If we have this kind of inputs, all 4 inputs are given to the gate, and we are getting this kind of output. All of them are given, you just think like that all of them are given together, okay, simultaneously on the gate. So look, we have to at least have some idea about this output, about the output or the truth table of the various gates. Like AND gate, you know, AND gate is actually, if you have A and B both on or both high, then output will be high. In case of AND, if one of them is low, then it will be low. This is for AND gate. Okay, this is AND gate truth table. Okay, so AND gate means AND gate output generally will right. Okay, generally output will be A dot B. Okay, that means if you just if you just multiply all of them, then what you get? See, this is low state. This is also low. This is also low. This is also low. If all of them are low, then you are getting output low during this time. Okay, if all are low. Okay, and see other state everywhere. See, just after this there is high here, H, this is low, high, low, H means high, this is low. So in this case it is L, this is high, this is again L, this is H, this is low, and this is high. Further we'll write L, this is H, this is L, this is H, sorry, this is low, low means L, and this is high. Okay, this is at least high. So you can see when everything is low, you are getting low. So everything is low means you are getting low. In case of AND gate, in case of OR gate, low. So OR gate will give you output A plus B. So here output will be A dot B. Okay, NAND gate, it is saying that when all the inputs are high, then you get low. So if both are 1 and 1, if so high high, I'll write high high, high high. Suppose there are two inputs, both are high, that means 1 and 1 produces low output. One of them is low, one of them is low, then output should be high. If any one of them is low, output should be high. And when everything is low, then also you should get high output. But you look here, when everything is low, X is low. This is low and this is high. So that's why it cannot be NAND gate. See now if you look this part, see this is high, but this is low, this is low. So both high and low combinations are there. So only thing is that a high low combination will give you high only when it is OR gate. Okay, low and high both are there. So if one is low, another one is high, then also you should get high input, sorry, high output. Excuse me. So in this case, this is not true. Not means when low, then you should get high. So it is also not true. So only thing is OR. So see here at this particular position, the low and high. Here also low. Here also low. So low, all three are low, but only one is high. So you get one high output because this is additive, kind of additive. Okay. So if one of them is at high state, your output will be high state in case of OR gate. Okay, so that's why it is like that. Okay, we have discussed this. Okay, we may take few more truth table just for recapitulation, practice and recapitulation. Okay, one more truth table maybe we'll take, one or two more truth table. So you have been given a truth table A, B, and this is, suppose Y is the output. So when it is 0, 0, this is 0, 1, 1, sorry, 0, 1. This is 0, 1. This is 1. Again 1, 0, 1. Okay. Then 1, 1. Also 1. So what is this gate? Whether first option is First option is given as AND gate, and gate. Second option is OR gate, and NOR gate, option C, and NAND gate. So in this case, look, if one is high, see, we know in case of AND gate, you have A dot B, this is X is equal to, OR gate, you get A plus B. NOR gate, exclusive NOR. So in case of NOR gate, if both are high, then only you will get output. In case of NOR gate, so OR, see, NOR means OR along with NOT. Let us say this. So if you have suppose here 1 1, so you get OR means you get 1 here. So then it will give you output bar. That means when you have both high, you will get actually low state here, low state. So both high means low, here you should get 0. So this is not NOR gate. NAND gate is actually AND along with NOT. So along with NOT. So if you get here 1 1, so NAND gate, NAND should actually give you AND plus NOT. That means A dot B and bar of that. So you should get A bar plus B bar. Okay. So A bar plus B bar. So in this case also both are high means you'll get low output. So this is NAND and this is NOR. So these are not true for this case. So this is not true, this is not true. Here this should be NAND capital. This and will not be there because this is 0 and 1 would give 1 only when this is OR gate. Okay, so this is how we have to solve. Okay, we'll stop it here for today. In the next class we'll start with wave optics, or wave plus this geometrical optics, both maybe we can take. So in the next class we will discuss optics part, questions from optics. Okay, so bye for today. Thank you for your patience.